Hello everyone. So today we're going to continue on 13.2. So our last video we get to see theorem 13.2.3 and 13.2.4 in action. So you basically want to do is set up a system equation to solve for b sub 0, the b sub j, the coefficient function, and then once you have that, you just basically put them together and combine to form your matrix. For the most part, we will stick with matrices that are 2 by 2. Maybe some cases we do 3 by 3, but it will not be a too massive matrix because I don't need you to be able to do a, let's say, 12 by 12 matrix to find e to ta. I just need you to understand the process and be able to do some basic one so that you know what you need to do. So our next example is going to be on a complex eigenvalue eigenvector. Okay, on a matrix that have complex eigenvalue eigenvector. So here's our next example. We're going to let matrix A equal to 1, -1, 1, 1. And once again, we're going to give you the eigenvalue because you should know how to find eigenvalue already. With eigenvalues. And one thing interesting that you might notice is that we don't actually use the eigenvector in this method, which is nice. Okay, with eigenvalue lambda 1 equal to 1 plus I, and lambda 2 is 1 minus I. Now, actually, did I use the, was it the example that we did? I don't remember. I don't think it is, but maybe it is. Oh, no, it's not. Okay. We might have used this matrix somewhere else. I don't remember. It does sound, does look familiar, but then again, you know, I don't know. Maybe. And the question will be the same as the last one. I'm just going to ask you to use theorem 13.2.3 and 13.2.4 to find e to ta. And you will have a question kind of similar to this where I ask you to use these two theorems. So you have to make sure you know how to use it. Alright. So A is a 2 by 2 matrix again. So therefore imply n is 2. Therefore tell me that e to ta is going to be just like the last one. B sub 0 times I plus B sub 1 times A. And once you have done a few of these, you remember this very simple pattern even when we do 2 by 2 matrix. And when you do 3 by 3, you just have one extra term. It's not a big deal. Alright, so once again, the important part is to try to figure out what is the b sub 0 and b sub 1. So we're going to try to set up our system equation. So when k is equal to 1, we know n is equal to 2. Therefore, we have e to t lambda 1 equal to summation j from 0 to n minus 1, which is 1. B sub j of t, e lambda 1 to the j. So therefore, in this case, that just basically equal to e to the 1 plus it would equal to b sub 0 multiplied by 1 plus I to 0 power plus b sub 1 times 1 plus I to the first power. So what would that turn into? Well, that turned to e to the 1 plus it would equal to 1 plus I to 0 power is still 1. So therefore just b sub 0 plus b sub 1 times 1 plus I. Notice that because we have complex eigenvalue, we actually end up with a complex equation. If k equal to 2, we know n is still equal to 1, n is still equal to 2. The formula from 13.2.4 become e to t lambda 2 is equal to j from 0 to 1, b sub j of t, lambda 2 to the j. So therefore become e to the 1 minus I t would equal to b sub 0 times 1 plus 1 minus I to 0 power plus b sub 1 times 1 minus I to the first power. So therefore this one will come out to be e to the 1 minus it equal to b sub 0 plus b sub 1 multiplied by 1 minus I. So now it's just a matter of using these two equations to solve for b sub 0 and b sub 1. So I think I'm not sure what to do, but I'm going to go and do this. I'm going to go and take the first equation. I'm going to take the second equation, but I'm going to negate it. And so now I can add them together. Then b sub 0 cancel out. And therefore what I have is e to the 1 plus it minus e to the 1 minus it would equal to b sub 1 times 1 plus I minus b sub 1 times 1 minus I. This was 1 minus I. And if you multiply this out, that just becomes b sub 1 plus b sub 1 I b sub 1 minus b sub 1 plus I b sub 1. So the b sub 1 actually cancel out and that leave it with I b sub 1 but twice. So therefore become 2 I b sub 1. On the other side, what would happen to e to 1 plus it and e to 1 minus it? Well, what I'm going to do is I'm going to rewrite them into sine and cosine. So e to 1 plus it becomes e to the t cosine t plus e to t sine t. And go minus, this is e to t cosine t. Because of negative I become minus e to t sine t. So if I look at this correctly, that would mean that this is a plus, this is negative, this is plus. So therefore, if I look at this correctly, the e to t cosine t just get cancelled out. Oh, and I forgot the I. Because e to the a plus bit become e to the at cosine t plus e to ati sine t. So let's see what we got here. So therefore, look to me that the two I e to t sine t will combine. So we become 2I e to t sine t equal to 2I b sub 1. Wow, look at that. The I and the 2 just simply cancel out. And therefore, leave me with something quite simple. B sub 1 equal to e to t sine t. So now I'm going to do is try to solve for b sub 0. So how do I proceed with that? I guess I could just take one of these two equations and just go with it and see what happens. I guess I just take this top equation and go with it. So e to the 1 plus it would equal to b sub 0 plus b sub 1 times 1 plus I. I already know b sub 1 already. So what I'm going to do is I'm simply just move that over to this side and say that b sub 0 would equal to e to the 1 plus it minus b sub 1 times 1 plus I. So therefore, that would mean that b sub 0 equal to e to t times cosine t plus I sine t minus b sub 1, which is e to t sine t multiplied by 1 plus I. So if I'm looking at this correctly, b sub 0 will be e to t cosine t plus I e to t sine t minus e to the t sine t minus I e to the t sine t. So look to me that the e to the I e to the t sine t would cancel out, and therefore leave me with b sub 0 equal to e to t cosine t minus e to t sine t, which is actually not that bad. So now with these two things together, I can now go and put e to ta together. That will be b sub 0i plus b sub 1a. So therefore, e to the ta would equal to e to t cosine t minus e to t sine t multiplied by 1001 plus e to t sine t multiplied by 1 negative 1 1. So what is e to ta equal to? Oops. So once again, you're basically working with two terms, e to t cosine t and e to t sine t. So the first corner, look to me, I have e to t cosine t minus e to t sine t plus e to t sine t. So it becomes e to t cosine t. The second term, I just have negative e to t sine t. The bottom, I only have e to the t sine t. And then at the end, I have e to t cosine t minus e to t sine t plus e to t sine t. So it becomes e to t cosine t. So sim to me, that's what e to ta is. That's our e to ta. Pretty neat. And that's kind of took less work than if we have to go through this whole process up here again. The tricky part about it is that once you get the matrix, you have to expand into sine and cosine and then combine all the terms and factor everything out. So that seems like a lot of work, but here it seems like it's less work, I guess. Oh, what happened? Oh, okay. Apologize. My OneNote is thinking. Oh, there you go. So now these two examples are not too bad. Okay, maybe using theorem 13.2.3 and 13.2.4 with complex eigenvalue. It might seem like a little bit easier, but none of these we cannot do before. Now let's try to see an example where we have repeated eigenvalue and see what happens. Okay? So here's our next example. We're going to let A equal to a matrix 0, 1, negative 4, negative 4. And with a repeated eigenvalue lambda 1 equal to lambda 2, which they both equal to negative 2. So once again, I'm going to ask you to find e to the ta using theorems 13.2.3 and 13.2.4. So here's the problem. The problem is that we have a repeated eigenvalue. Now, however, it doesn't change what we need to form the solution. 13.2.3 still applied exactly the same, which for a 2 by 2 matrix is telling me that e to ta is equal to b sub 0 times I plus b sub 1 times a. So that's the formula that we're working with. The tricky part is how do we find b sub 0 and b sub 1 now that we have a repeated eigenvalue? Okay, so let's see. So first of all, regardless of what happened, we do have a repeated eigenvalue, but we at least have one eigenvalue, which is negative 2. So therefore, based on 13.2.4, it tells me that e to negative 2t must equal to summation j from 0 to n minus 1, which is 1, b sub j of t, negative 2 to j. So that's plugging either lambda 1 or lambda 2. And so therefore result in this equation, e to 2t equal to b sub 0 minus 2 b sub 1. The problem is I cannot use the same equation twice because that doesn't give us additional information. And with just one equation on this we have right now, we won't be able to solve for b sub 0 and b sub 1 because they will be changing according to each other, and we won't be able to find a fixed answer for that. That's where we stuck. Unfortunately for us, theorem 13.2.4 has a condition that allow us to deal with this. Okay? So let's try to understand what happened to theorem 13.2.4 and what does it tell me to do. So theorem 13.2.4 is saying that if we have a repeated eigenvalue, we have to basically use this formula, okay, to find actual equation. For us, we only have one repeated value, okay, which is lambda 1 equal lambda 2. So in this case, basically, I'm saying that m is 2. So therefore, I would just simply using one value for just k equal to 1 to go through this process. And it's nice because that means I only have to take the first derivative, which makes sense because I only need one extra equation. So if I take derivative once, I'll have that one extra equation. If I need two, meaning that we have a 3 repeated eigenvalue, that will need to have 2 extra equations because notice we have 2 repeated eigenvalue. That means we have 1 equation short. 1 less than the number of repeated eigenvalue. So now if I just simply take the derivative, I'll be able to do this. So what would that be? So the tricky part to use the second part of the equation correctly is to not put in lambda yet, but actually figure out what the derivative look like first. So according to theorem 13.2.4, what we're basically doing is e to t lambda equal to summation j from 0 to 1 b sub j of t lambda to j. And therefore result in this equation, e to t lambda is equal to b sub 0 plus lambda b1. Now here comes the important part, the theorems. So once again, take a look at theorem 13.2.4. It tells us to take the derivative, but here's the important part. Differentiating what? We actually differentiate with respect to lambda, not t. Okay? So what happens if I take this equation that we have, which had lambda and t in it, and take the derivative with respect to lambda? Well, simple. Then in this case, when I take the derivative with respect to lambda, we're treating t as a constant. So therefore, it becomes t e to t lambda equal to b sub 0 would be a function of t. But t is constant. So therefore, b sub 0 will actually be a constant function. So therefore, it becomes 0 plus b sub 1 will be a constant function in terms of lambda, so it's staying, and I differentiate lambda, which I get 1. So this is very tricky because you have to remember that b sub 0 and b sub 1 are both functions of t, but here we differentiate with lambda. So basically treating this equation right here, technically speaking, is this should be written this way. And so therefore, we treat it as like 2-variable equation, where the 2 variables are t and lambda. And then I'm going to kind of like taking a partial derivative, actually. Now that I think of it, maybe I should have written it as a partial derivative so that it makes more sense. But you know what, actually it's probably okay because we're actually not like doing partial derivative. We just basically treat this equation where t is constant and lambda is a variable. And so if you look at this, that actually come out pretty neat because this simply just tell me t e to t lambda, which is equal to b1. And so for our repeated value, lambda is -2, so therefore t e to -2t would equal to b1. That's actually pretty good because that actually solved for one of them already. So now I could go for solving for the second one, which is b sub 0, and since we know b1, I can just simply use this formula to find b sub 0. So it seems to me that b sub 0 would equal to e to 2t plus 2b1. So therefore b sub 0 would equal to e to 2t plus 2t e to -2t. Oh, -2, I missed a -2 here. And that gives me b sub 0. So that's actually easier compared to I have to solve a system equation, which is nice. So now I can go ahead and try to plug into my formula. So I'm going to go for it. So e to ta would equal to b sub 0i plus b sub 1a. So therefore would equal to e to -2t plus 2t e to -2t multiplied by 1001 plus t e to -2t multiplied by the matrix 0, 1, -4, -4. So therefore e to ta would equal to so because there's 0 in the second matrix, this first term on the top left would just be e to -2t plus 2t e to -2t. The second term right here would just be, because it's 0 in the first matrix, it would just be t e to -2t. The bottom one would just be -4t e to -2t. But the bottom right is now require a little bit of work, so if you think about it, it would just be e to -2t because the second matrix doesn't have a e to -2t term, and then for t e to -2t I have 2 minus 4, so become -2t e to -2t. So if I pull out the e to -2t from all of them, then I actually have this matrix. So that would be our answer. Alright. So, the last thing I want to show you is the following. The last thing is actually quite neat. Notice that when we're using Theorem 13.2.4 and 13.2.3, well actually 13.2.4, 13.2.3, it would require me to actually use the power of A. Now, granted, I don't need it to go on to infinity and form some kind of pattern, but I still need to be able to relatively quickly generate powers of A, because the formula for 13.2.3 require me to form this summation that is a polynomial of A to n minus 1 degree. So if we're doing a big matrix, let's say a 5 by 5 matrix, then I will have to do a polynomial of degrees 4, which means I do need to know how to find the matrix A to the 4th power. Now, for a 5 by 5 matrix, that's actually quite a lot of calculation to do. And granted, our calculator can probably easily do that, but I would like to show you a very cool way to calculate a matrix to a square matrix to high power, by using a simple process that actually just multiply them out. Show you. This is Theorem 13.2.5. And hopefully I have enough time to show you what the theorem is. Let's say given an n by n matrix A with a characteristic equation. What is the characteristic equation? That's the equation you use to find eigenvalue. With a characteristic equation P of lambda equal to the determinant of A minus lambda I, which is equal to 0. Well, actually, I'm not going to set it equal to 0, but that would be the characteristic equation, which is basically the determinant of A minus lambda I. That's what we use to solve for lambda, which is the eigenvalue. Then the tricky part is the following. Then the matrix polynomials missing the word matrix. And what is a matrix polynomials? Is basically meaning that you put a matrix into a polynomial function, which is exactly what we have right now. The matrix polynomials are obtained by substituting A for lambda in the formula P of lambda will satisfy the equation P of A is equal to 0. And of course, when I say 0, I mean the 0 matrix. Okay? Now the question is, then how does that help us forming the power of A? Well, actually, show you a very simple example. Let's A equal to the matrix 1, negative 1, 1, 1. Okay? I'm going to ask you to find, let's say, A squared using theorems 13.2.5. So, I mean, I know this really doesn't require me to use any theorem. I can just say multiply matrix A by A. I'll get an answer. But to show you what cool thing about it. So first of all, I'm going to do is I'm going to go and find my polynomial P of lambda, which is equal to the determinant of A minus lambda I. So therefore become the determinant of 1 minus lambda, negative 1, 1, 1 minus lambda. And therefore become 1 minus lambda times 1 minus lambda plus or minus 1 times negative 1. So that come out to be lambda square minus 2 lambda plus 1, which is 2. So this is my P of lambda. That's my polynomial function, which is what we call the characteristic equation. And when we set that equal to 0 and solve for lambda, we get the eigenvalue. Now look what happened. If I now plug in the matrix A, that would equal to A squared minus 2A plus 2, which in this case I can say plus 2. I'm going to say plus 2I. And we know that based on theorem 13.2.3, it will satisfy the equation equal to the 0 matrix. Now, here's an interesting thing. If I look at this equation right here, this equation actually has 3 different matrices involved, A squared, A, and I. We know what I is. That's the identity matrix. We also know what A is, because A is the matrix that's given to us. So if that's the case, then would it make sense I can actually solve for A squared by simply just plugging what we know? So in this case, I can say, well, A squared will simply equal to 2A minus 2I by say moving those 2 matrices to the other side. And therefore meaning is 2 times 1, negative 1, 1, 1, minus 2 times 1, 0, 0, 1. Notice that this bypass matrix multiplication and allow me to easily figure out what the matrix A squared is. A squared is actually equal to 0, negative 2, 2, 0. Now, the interesting thing about it is that I can actually use this to recursively find higher power of a. What if now I want to find a to the third? Well, yes, I know I can just take a times a squared, but how about we do this? Well, a to the third is, technically speaking, a times a squared, and we know a squared is 2a minus 2i. So therefore, tell me that that's just 2a squared minus 2a. And just so happen we know a squared already, so I can just plug that in. That will be 2 times 0, negative 2, 2, 0, minus 2 times a, which we know is 1, negative 1, 1, 1. And so, if I do it correctly, a to the third would equal to negative 2, and negative 4 plus 2, which is also negative 2. 2 times 2 is 4, minus 2 is 2, and negative 2. I know the video is a little long, but I just have one more thing I want to show you, and that would be it. Now, this theorem go beyond finding a powers of a. Granted, it still recursively generate power of a, but it bypasses something that requires a lot of calculation, and that's matrix multiplication. This allows us to actually form a power of a into a linear combination of power before it, which is pretty cool. But what's even cooler is, what if I want to find a inverse? How do we go about doing that? So for a 2 by 2 is not as impressive because we do have a formula for a 2 by 2 matrix inverse, but for higher power matrix, this becomes an extremely cool way to actually form the inverse or matrix. So this is how we do it. We know that a squared minus 2a plus 2i is equal to 0, and therefore imply that a squared equal to 2a minus 2i. Assuming a inverse exists, I can actually multiply this entire equation by a inverse. If I do that, a inverse times a squared will just become a. And a inverse times a inverse become identity. But what is a inverse times I? That become a inverse. So now once again look at this equation. This equation will lay three matrices together. A, I, and A inverse. But we already know I, because of the identity matrix. We also given A. So now all I have to do is solve for A inverse. So I can say A inverse would be I plus, or I minus 1/2 A. By simply move it over and divide by 2. And now I can simply put in I, which is 0, 1, 1, 1, 0, 0, 1, and then I can plug in A, which is 1, negative 1, 1, 1, and with a negative 1/2 in front, I will now be able to find out that A inverse is 1/2, 1/2, negative 1/2, 1/2. Now you can verify that answer by using the inverse formula, and you'll find out that you get the exact same thing, which is pretty neat. And of course, as I say, this formula or this method is not very useful for 2 by 2 matrix, because it's probably easier to just multiply the matrix together or just use the inverse formula. But for large matrices, it becomes a lot easier to actually do because it simplifies a lot of calculation. Why? To find a, let's say, a 5 by 5 matrix, multiply a 5 by 5 matrix, you have to do 25 dot products. Okay, and each dot product requires like 10 operations to do. That's a lot of operations that you have to do. As a matter of fact, the operation require grow almost factorially. But doing this way would keep the number of operations that you do grow linearly. So therefore, even with a really big matrix, you still require very few operations. Alright, unfortunately my time right now, but this is technically the end of 13.2 for us. So therefore, our next video will start on 13.2.3. Alright, I'll talk to you guys in the next video. Okay, bye-bye.